As Bill mentioned, I'll be talking about the Statistical Severe Convective Risk Assessment Model, an acronym that you probably cannot remember relatively well, SCRAM. You don't need to leave the room, though. This is a system that John Hart, SPC lead forecaster, has developed and has graciously included me in terms of this project. So a brief overview of what SCRAM does in a single statement. This is a system that relates current meteorological conditions in proximity to thunderstorms, so talking about near-storm environment, to short-term forecasts of severe thunderstorms downstream. So looking at what does a certain mixed layer CAPE value of 585 joules per kilogram mean in the context of lightning being produced in terms of downstream severe weather threat. Looking at the period from 2006 to 2014, and then we'll extend this forward in terms of real-time operational implications shortly. So in this endeavor, we're combining Storm Prediction Center mesoanalysis data here during the period of 2006 to 2014, looking at the lower 48 states, all of the kinematic, thermodynamic parameters that are associated with severe weather threat, potentially, and many other parameters as well in that 2006 to 2014 timeframe, merging that with actual CG lightning strikes from the NLDN database. As you can see, an example here, merging environmental information with those lightning strikes, along with what actually happened in terms of severe thunderstorm reports, damaging winds, large hail, and tornadoes. In terms of making some assessment, environmental assessment, merging with known thunderstorms, and then what actually happened in terms of severe weather. Let's talk about how this model actually operates, some of the nitty-gritty details. Let's consider portions of southwest Missouri, northeast Oklahoma, and vicinity here, and we'll drop a 40-kilometer RUC2 wrap grid on the background domain here as an example over here. And you can see the various grid boxes highlighted in red in the background. And suppose during a 1-hour period, which we'll call an initial hour, we have a cluster of lightning strikes occur within a few of those grid boxes in far southwest Missouri over here. I'm now going to highlight the specific grid boxes that specifically coincided with the presence of lightning strikes so that we can specifically highlight those boxes that are candidates for potential downstream severe thunderstorm occurrences, or lack of occurrences, but which we'll focus on shortly. And now let's look at some of the environmental assessment characteristics on that middle grid box in the right column over there with a cluster of strikes. And we're going to consider in the SCRAM system documenting various properties of that grid box, date, time, center point, number of strikes. But very importantly, bunker storm motion to get some idea about downstream storm trajectory, where a storm may end up being within the next 1 to 2 hours, for instance, as well as the environmental conditions from the SPC mesoanalysis system characteristic of the near storm environment for that grid box. Now, this is done for each and every grid box across the entire country for lightning strikes all the way from 2006 to 2014. A lot of information there. And when we do that, we're focused on that one grid box, for instance, as I'm showing this example. Within that initial hour, I'm going to put an X here indicating the center of that grid box in which we had lightning occurring. And then we're going to project a storm motion forward using Bunker's supercell motion technique to get some idea of a forward trajectory of that supercell launched, assuming a supercell here, launched from that center point of that grid box over there, and then look at, within that hour, midway through that initial hour, what that storm position might be, and then search within 40 kilometers of that projected forward location to see did any severe weather reports occur in association with that storm within that first hour. And then we'll proceed to the second hour, that one subsequent to the initial hour, forward extrapolate that storm downstream using the Bunker supercell motion technique, and then search within 40 kilometers of that downstream estimated storm position to see if any severe weather reports occurred. So we're doing this now not only for every single grid box with environmental conditions, but projected forward in time and space storm locations for every single one of these grid boxes across the United States over a long time period, nearly a decade. And the result is going to be a tremendously large data set here from which we'll be able to relate those initial hour environmental conditions with lightning strikes to severe storm report occurrences and nulls as well, in which we don't get large hail damaging winds or tornadoes occur. And through collecting, pooling all of that information together, we can generate probability distributions of severe weather hazards hail, wind tornadoes based on various parameter ranges characterizing those initial hour grid boxes that have the related environmental characteristics. This is one of the most comprehensive data sets for severe weather forecasting with a sample size of over 3.8 million lightning and environment grid hours to do a lot of work with, where again, the idea here is to relate downstream severe report occurrences with diagnostic, the initial hour, initial time, parameters, and presence of lightning, so some conditionality here. And we're also considering null events at the same time. So in short, we're exploring the use of diagnostic parameters in a predictive or prognostic manner here, which is really trying to accomplish a challenge set out by Doswell and Schultz 2006 in terms of expressing some prediction of future impacts, severe weather impacts from the present atmospheric state. Ultimately, down the road, we could see this type of analysis system being used in terms of assisting with warn-on forecast initiatives as well as facets initiatives. All right, so now let's take a look at what some of these results actually look like for the 2006 to 2014 time frame. And we'll start out by looking at a basic measure of buoyancy here, MU CAPE. And I'm going to be showing relatively similar plots for various parameters. And there are going to be a couple of curves I'll be focusing on. And we're going to describe what those curves mean on this particular plot and then extend it forward to a number of different variables. So starting with MU CAPE here, I'm going to start out first by talking about this black probability curve. It's a conditional probability curve. As we go to the right along the x-axis, we have various ranges of MU CAPE values, 0 up to 250, 250 up to 500, et cetera, going to the right there. And the conditional probability plot, specifically in this case corresponding to severe thunderstorm winds occurring downstream, is shown in black there. So for a given range, for instance, of MU CAPE, we're looking at the probability of severe wind reports occurring within various parameter ranges plotted along the x-axis, given the conditions of lightning occurring in the grid boxes and any other constraints, which I'll be listing at the top. In this case, no other constraints, but you'll see a couple examples shortly where we do include some other constraints, for example, to focus specifically on grid boxes supporting surface-based organized convection. And as such, with many grid boxes potentially being associated with these MU CAPE values not producing severe weather, we have null reports, or I should say null cases, that are incorporated within the data set, allowing us to generate these conditional probabilities. So an interpretation of one particular range bin over here, 2.6%, looking up here to the conditional probability curve of 500 to 749 joule per kilogram MU CAPE environments, given the constraints, lightning occurrence, for instance, are severe wind producing environments over here. So that tells us some conditional probability for severe wind linked to that range of MU CAPE values looking forward in time and space. Now there's another curve we'll be focusing on here, and it's in blue. This is what we'll call the relative frequency of severe environments. We're specifically focusing on severe weather events that occurred and looking at the partitions of those severe weather events, wind, hail, and tornado, occurring within various ranges of those parameters, as shown along the x-axis here. So again, proportion of severe producing environments associated with these parameter ranges, specifically focused on, in this case, severe wind reports. Let's talk about an example, for instance. Looking at MU CAPE once again, severe wind, looking at 500 to 749 joules per kilogram, 7.3% of severe wind producing environments are associated with MU CAPE in the 500 to 749 joule per kilogram range. So we can see where there's a tendency for this particular severe weather hazard to occur within various ranges of the parameter values listed. So that'll be the overall structure, as I'll be showing in this presentation, of how these plots are going to be presented. So one natural question you might say, well, what's the meaning of this black curve in terms of predictability of a given phenomenon based on a predictor value or a set of predictor values? What does good predictability look like? What does not so great predictability look like? We're going to answer that or address that question with a few hypothetical examples over here. What lacking predictability might look like. So say we are trying to predict some phenomenon over here using a predictor with ranges of values along the x-axis here and probability occurrence proportions up here along the y-axis. Now suppose that the conditional probability curve that we get in this particular case is a flat line over here, such that any change in the predictor value that we'd be using corresponds to negligible or no change in the actual probability value, effectively a flat line. This demonstrates, as we'd expect, little predictability in this particular case. If I gave you an MU CAPE value of 500, get the same probability of 5,000, for instance. That's not necessarily useful over here. Another case of not great predictability would be a very steeply sloped curve. For instance, this one shown over here, by which very small and measurable changes in the parameter value, perhaps related to instrumentation error, forecast uncertainty, etc., small variations in the environmental state correspond to vastly different probabilities, suggesting a very sensitive parameter over here. And that could also present some problems as well. So what would good predictability look like based on a given predictor value? We're going to look at the case where we have a noticeable slope over here, such that we have incremental increases in probability values with incremental changes in the predictor ranges, for instance. For instance, in this graph over here, we see increasing parameter values with increasing probabilities, noticeable signal over here, and it's not too sensitive. So this would be a demonstration of what a good predictability looks like. Now let's apply all of this together by looking at a series of different parameters, forecasting different hazards, and then we'll build this up to looking at significant tornadoes. So let's go back to using MU CAPE in terms of forecasting severe wind and severe hail. Severe wind in this top plot over here, severe hail in this lower plot over here. And you can see in both of those cases the probability of both severe wind, black here, and black here in the lower panel, severe hail, increase with greater amounts of MU CAPE. Makes sense. Conditional probabilities are increasing in the presence of lightning with greater amounts of buoyancy. Also, it's very interesting to note here that the majority of documented severe wind and hail events tend to occur at MU CAPE values below 3,000 joules per kilogram. Effectively, the critical mass under this blue curve over here is at MU CAPE values that are below 3,000 joules per kilogram. Of course, that just means that environments producing severe storms tend to occur more rarely at these high values, although the conditional probabilities associated with lightning with higher buoyancy correspond to greater chances for severe wind and hail. Effective bulk shear, toggling between MU CAPE and effective bulk shear, there's overall a tendency for a bit better utility overall in terms of using effective bulk shear, a parameter that Rich Thompson developed in this citation over here, to be serving as a conditional forecast parameter for both severe wind and hail. A little bit steeper. All right, and so we see that relatively similar, although steeper slopes for the effective bulk shear. Now let's take a look at those severe environment relative frequency curves for severe wind. We're going to focus now, again, on severe wind specifically, and look at the relative frequencies where these severe wind environments tend to occur using effective bulk shear as a predictor. And we're going to constrain the data set into various ranges of MU CAPE as shown by the variations in color coding here, such that greater amounts of MU CAPE, for instance, 3,000 to 4,000 joules per kilogram, are shown in the darkest blue, with lighter blue corresponding to the 0 to 1,000 joule per kilogram range. And again, this is severe environment relative frequency for severe wind. And what we see is pretty interesting. With increasing values of MU CAPE, we're looking at those darker blue curves, there's a tendency for the severe wind reports to occur more frequently with lower values of effective bulk shear. The peaks in these curves, the overall distributions are overall shifting to the left or towards lower values of effective bulk shear with greater amounts of MU CAPE. And this is consistent with what we see operationally, kind of a rarity for high buoyancy to consistently overlap with strong amounts of vertical wind shear in severe wind-producing environments. The overlap is more of a rarity overall. Now let's shift gears to start looking more at tornadoes right now. And we're going to show mixed layer lifting condensation level heights, MLCLs. And now we're going to add in some constraints to specifically look at those lightning-producing grid boxes that are associated with the potential for surface-based organized convection. We'll express that as ML CAPE values in excess of 1,000 joules per kilogram, effective bulk shear of at least 50 knots, and mixed layer inhibition less negative than negative 50 joules per kilogram. And we can see here that a couple things. For instance, for both weak tornadoes, which we're showing up here in this top plot, and significant tornadoes in this lower plot, so combination for any tornadoes, this blue curve, the severe environment relative frequency curve, tends to peak more and favor more of an optimal range in the 500 to 1,100 meter range, typically. And those are the values that we typically associate with tornadoes, significant tornadoes, weak tornadoes. And so the bulk of the distribution of these tornadoes tends to occur within 500 meters to 1 kilometer. But interestingly, if we look at the conditional probability curves in both cases, they're relatively flatlined over here using MLLCL and relatively low. They're hovering around relatively low values overall, which is suggesting that many environments that support surface-based organized convection, these constraints over here, that also have those low favorable MLLCL values actually result in null cases over here. Now, this is in the absence of considering values of effective storm relative helicity, which shows a much better signal. But using MLLCL alone, combined with these constraints for surface-based organized convection, shows a relatively diminished muted signal overall in terms of both weak tornado and significant tornado predictability downstream using the Scram model. Now we're going to focus more on significant tornadoes right now. And I'm going to refer to a parameter that's treated as the gold standard in meteorology in terms of forecasting, analysis, the significant tornado parameter developed by Rich Thompson here. This parameter, which we have plotted along the x-axis in various ranges over here, would correspond, as we'd expect, to increasing potential for significant tornadoes downstream. And indeed, using the conditional probability curve here in black, and I'll also mention we have an exceedance probability curve shown in this dashed maroon line, and that corresponds to probability of downstream significant tornado occurrence occurring within various STP ranges of at least the values listed along the x-axis. We can see a general increase in probabilities of significant tornadoes with higher STP values going to the right. Certainly no big surprise at all, but I want to point out a couple things here. As you can see, when we get to values of STP of at least 10 to 11, which we sometimes see in the presence of supercells, we're dealing with conditional probabilities of 20%. Now, when you think about a 10 hatched Tor area in the convective outlook, we're talking about 10%, and that's usually pretty substantial in terms of overall impact, in terms of overall threat. Now, we're talking about double that when we're looking at these STP values of at least 10 to 11, which is pretty significant overall in terms of threats. And now this, again, looks at the entire distribution of Scram from 2006 to 2014. And one aspect of Scram is that not only there's a lot of flexibility, a lot of versatility in this particular data set in which we can look at not only the parameter ranges that we use in terms of forecasting, we can look at various regions of the country, different time periods. We can look at a lot of different attributes that are linked to those grid boxes.